some earlier work we did in extending the graphical architecture to handle rules. So what I'm going to do is start by giving you a brief intro to Sigma and its graphical architecture, talk a bit about what it takes to extend this to rules, and then move on to the newer work on neural networks. So Sigma, the development of Sigma is driven by 4 general desiderata. There's grand unification, which says we want to go beyond just unifying the standard kind of cognitive capabilities to include the key subcognitive capabilities that are also involved in yielded intelligent behavior. Generic cognition, that says that we're looking to span both considerations and modeling across both natural and artificial cognition. Functional elegance, where what we're trying to do is to build these systems by starting with a small general set of primitive mechanisms and getting the diversity of intelligent behavior by the interactions among those mechanisms. And sufficient efficiency, which says pretty much what it is, that is, needs to be fast enough for the kinds of applications we're anticipating. So ultimately, we're trying to get to a system that can think, that can behave appropriately both in physical and social environments, and mixtures of those, and learn appropriately from its experience. I'm going to talk a little bit more about functional elegance because it's one of the things that's more unusual about Sigma and also strictly relevant to the work I'm talking about today. So let's talk about modular versus functionally elegant approaches to building cognitive architectures. So you're all, I seem, familiar with the traditional modular approach. You build a set of modules for memories and learning algorithms and so on, with a well-defined set of interfaces between them that lets you draw a nice diagram for it. Standard engineering approach to building any kind of computer system. In contrast with, well, here's a couple of examples. So SOAR, which you saw in John Laird's presentation, ACT-R, they have different sets of modules, but they both follow this kind of general pattern. Functional elegance, in contrast, tries to dig down below that set of modules to find what's the commonality that then gives rise to the capabilities provided by those modules without necessarily making them distinct modules. So from what we've seen this week, I believe that both ART, which Steve Grossberg talked about, and NARS, that Pei Wang talks about, are striving for forms of functional elegance. They're going for uniformity in another sense. And AXI is a rather extreme point on this, where it tries to get all of intelligence from a single equation. So the goal here is to improve the elegance, depth, and breadth of cognitive architectures, or AGI architectures, as we do this. The other thing that's particularly unique about Sigma is the approach it takes to building essentially a new generation of architectures. The idea is to blend what we've learned from over 3 decades worth of experience with cognitive and AGI and robotic and agent architectures with what's been learned independently from over 3 decades worth of work in graphical models. Hopefully you're all somewhat familiar with graphical models, and I'll talk a little bit more about them on the next slide. But roughly, they're a highly efficient technology that stays still theoretically elegant, but can provide state-of-the-art algorithms across a variety of different areas. So that's what makes them kind of interesting from an architectural perspective. So graphical models, again, in very brief, they're about efficient computation with multivariate functions. Here's a multivariate function, it's an algebraic one. But it's an example of a kind of multivariate function you can handle in a graphical model. We'll see many different kinds of ones in cognitive architectures. So what you do is you decompose this into a product of simpler subfunctions using usually some form of independence to do this appropriately. So here's a way of decomposing this particular multivariate function and then just labeling it as 2 different factors. You then map it onto a network of nodes and links. And there are many different flavors of these. Bayesian are the most familiar, but there are other forms. So for example, this is a factor graph, which has variable nodes for the variables and a factor for each of the factors in the equation, and has bidirectional rather than unidirectional semantics on it. So that's just one way of doing this. You then solve typically via some form of either message passing or sampling, though there are other things like variational approaches and so on. And that's roughly what a graphical model is about. On the next slide, I'm going to tell you a little bit more. Well, let's see, before we get there, I keep getting ahead of myself. So the key thing here is we get state-of-the-art performance across symbols, probabilities, and signals. all from a uniform representation and processing algorithm. And that's what we're going to make use of to get functionally elegant intelligence. In Sigma, we're using factor graphs, which are the most general form of graphical models known, and a form of message passing called the summary product algorithm. I'm going to tell you a little bit about that algorithm on the next slide, because again, what we're talking about here is going to depend on that. So the summary product algorithm. Here again, we have our equations, we have our factor graph. What we're going to do is compute either marginals on the individual variables, so that means a distribution over the variable with all the other variables summed out, or a mode over all of the variables. Okay, what would be a map estimation in probability. Mostly we'll focus on marginals, but we'll see some of the others too in Sigma in general. So we want to compute marginals, for example, the marginal on y given x and z. So what we do is we pass messages along the links. Those messages always have the semantics of being distributions over the variables on the link. So messages in either direction on this link are about x, either direction on this or this link are about y, on this link they're about z. Then at variable nodes, what we're going to do is we're going to compute the product of the messages. It's called a pointwise product. And at factor nodes, we're going to multiply times the factor and multiply all the messages together, and then we'll summarize all of the messages not needed. So the message from x to y, or from this node to y, doesn't need x, so we'll summarize out x. So as we look at that message from x, which is 3, which is just this one bit here, multiply, summarize out x, get a message on y. Over here, do the same thing, get a message on y, and then you multiply those together to get the marginal on y. That's fundamentally what's going on here in these kinds of systems. Okay, let's move up now to Sigma as a whole. So we talked about cognitive architecture and graphical models. And the graphical architecture hypothesis that combines those two. The structure of Sigma is going to take care of that. So Sigma is structured in layers, much like a computer system, where the two key ones we're going to care about here are the cognitive architecture and the graphical architecture. If you want to think about Alan Newell's timescale figure that John Laird provided, the graphical architecture is roughly at the lower end of the cognitive band, and the graphical architecture is the upper end of the biological band. So when he showed Sigma, he showed it going kind of from the upper part of the biological on up. Okay, so the cognitive architecture provides the language in which you build knowledge and skills. Predicates provide a relational language over terms and variables. Conditionals let you specify patterns of those predicates and combine those patterns in various ways. And then there's a control algorithm in which the inner loop is what's called the cognitive cycle. Now this maps roughly onto the 50-second or 50 millisecond cycle that we find in humans. John talked about 50 or 100 milliseconds. We'll normally talk about 50 milliseconds, which in Sigma structured is input followed by elaboration, adaptation, and then output. Elaboration is a variety of things, including accessing long-term memories, processing perceptual information, reasoning, and so on. That all happens in here. Adaptation then makes decisions, it learns, does other things like appraisals for emotion, attentional mechanisms, and so on. When we get to the graphical architecture, that's where graphical models come in. Some other stuff, including the learning algorithm that's down there. The key thing, though, is that the graphical architecture actually implements the cognitive architecture. So elaboration is completely accomplished by solving graphs, adaptation completely accomplished by modifying these graphs. Okay, what sets graphical models apart from most other forms of graphical models or architectures, and we've seen a variety this week and in other kinds of systems, is that there's a fixed semantics associated with a graphical model, including a factor graph. So what does that mean? So the semantics of the graph is defined by the expression, the multivariate function that you're trying to evaluate. The graph is correct if it accurately represents that expression. It's incorrect if it does not. Now you can use those semantics top-down or bottom-up. Top-down, like we did, take the expression, decompose it, map it onto a graph. Bottom-up, you build a factor graph according to the rules, and then you can induce what function that computes from it. So you can do this either way, but the important thing is that there's a semantics for the graph, which is separate from the graph itself. What that allows is, in fact, you can modify the solution algorithm, in fact, use a variety of different solution algorithms, as long as it reflects the semantics, either exactly for exact solution algorithms or approximately for approximate solution algorithms. So for example, for message passing, we can drop messages if we know they're not going to affect the outcome, and we can re-implement the computations of the factor nodes as long as we know they're going to compute the same thing, but do it in a more efficient way. Or again, use radically different algorithms. But the question that's come up in this work is what happens if you modify the algorithm in ways that go beyond the semantics? And it took us a while to actually understand that we were doing this. You can think of that as possibly leading to an extended factor graph, which is how we thought about it for a while, or as in fact what you have is an extended solution algorithm, like an extended summary product algorithm, where factor graphs are just one of the graphical idioms supportable by it. So restricting this extended algorithms in certain ways yields factor graphs, but other variations on it yield other kinds of models of computation. And this is kind of where we're going with this. So this is what's leading to a rethinking of Sigma's graphical architecture, essentially from the notion of an extended factor graph to an extended solution algorithm. So why extend the algorithm? Well, there are good reasons to. We expand it in order to expand essentially the breadth of the cognitive architecture. Now, graphical models by themselves yield lots and lots of relevant behavior. It turns out they don't yield all that I think at least needs to be there in the cognitive architecture. So the judgment was we needed to expand beyond it in certain ways in order to get some of the kinds of behaviors that we wanted out of the cognitive architecture. And if you're going to do this, again, functional elegance dictates what you want to do is do this in as functionally elegant way as possible. That is, if we want to add rules, for example, we don't add a rule module. We try to find the smallest changes down at the bottommost level of the system, which, when we change that, will allow us to do rules, but slight variations of it yield graphical models and perhaps other kinds of computational models as well that are going to be critical. So we want these small changes and kind of as far down as possible so we can share as much as possible. That's the game. So what we're going to do is sacrifice some semantic elegance in service of what can be considered algorithmic or procedural elegance. Again, it took us a while to realize that this is what we're doing. You can also think of this trading off declarative versus procedural elegance. Perhaps if we understand all of this well enough in the future, we'll be able to have both. We've made some effort to do that. Abram Demski, my student, who's one of the authors on this, really cares about semantic elegance and cleanness. We weren't able to figure out a way of doing that here, but he's developing a different architecture that might yield something like that. But ultimately, there's a hope for that. In the meantime, to continue making progress, we sacrifice a bit of the semantic in service of this other form. Okay, so let's look at an example of what this means in rules. So here's a simple transitive rule for above. Here's roughly what it looks like in Sigma. This is a somewhat cleaned up version of Sigma's list of semantics. So this is a conditional. It has 3 patterns on predicates. 2 of them are conditions, 2 of them are actions, and A, B, and C are variables in particular positions in those predicates. So this does the obvious thing. So that then gets converted into a graph. So we compile it into a graph using the read algorithm, which is the standard algorithm for rule match, but also adding actions into these graphs. And essentially in what we used to call extended factor graphs, you can then do the match and actions of the rules. I'm not going to go into details of this. This is covered in various papers in the past. But if you want to see how then the summary product works here, this is kind of a generic 2-rule system. These are the kinds of things that we've had to add to the basic factor graph version of the graphical architecture in order to be able to support these kinds of rules. So going beyond the bidirectional links, you find in factor graphs 2 unidirectional links, so we can get the one direction of message passing in conditions and actions. Going beyond the open world semantics, which are standard in graphical models, to closed world semantics, which you need in rules. Going beyond random variables to universal variables, where any number of them can be true. Any number of the elements can be true. We haven't gotten rid of the original things, but we provided these as alternatives. Filter nodes, which provide constant tests and things like that. And transform nodes, which essentially transform directly the range or the functional value of a function in order to do things like negated conditions. We're going to see this pop up again when we get to neural networks. It's an extension, though, of normally what's going on in a factor graph. So these are the kinds of extensions we made in service of rules, and they gave us a broader summary product algorithm, or graphical model, but not quite a factor graph when you make these kinds of changes to it. All right, what are the implications of this? So the graphical architecture now provides a procedurally elegant combination of rules and factor graphs. They both operate in these same graphs, but there are some variations in how parts of those graphs operate. Each is thus essentially a graphical idiom that depends upon specialization and combination of the basic extended summary product algorithm. So once you have this perspective, then the notion is additional small extensions might yield important additional extensions to overall functional cognitive behavior. Though ultimately, if you want this to be a cognitive architecture, this set needs to be fixed, or it has to be learnable. You can't just keep adding them over time by hand by a person, or you don't really have a cognitive architecture, which is a hypothesis about the fixed structure underlying cognition. So at some point you can say it's incomplete now, it will be complete at some point with a finite set of these extensions, but they have to be finite, and eventually you have to stop. So what we get, though, is that feed-forward neural networks are one of these small extensions. So I assume you all know about feed-forward neural networks. It's hard not to at this point. We have nodes and weights. We have messages moving or signals moving forward from inputs through hidden units to outputs. We compute weighted sums at inputs and then do a nonlinear transformation. That could be a sigmoid. It could be a hyperbolic tangent, and then I forgot what the RE stands for. It's not restricted. It's rectifier, so it's a linear rectifier. It turns out, factor graphs are known, a number of neural network algorithms map directly onto them. Certain forms of Boltzmann machines, for example, radial basis functions. Feed-forward neural networks do not. And as I understand it, the key reason they do not is because of this nonlinearity directly transforming the functional values, that is the range of the function. That is not what a normal function in a factor node does. A factor node function creates a function on the domain of the function. It doesn't muck with the range of the function directly. That's what this has to do, though. So it turns out, though, it's supportable, if you don't worry yet about learning, with just a new flavor of the transform node. Earlier I said that was used for negated conditions and actions for a logistic function. That's basically standard logistic sigmoid function. And then extending the cognitive language to express this. So, example. Here we define a couple of types. I should have predicates or over type variables. This one just says we have two element integers, so 0 and 1. Here we have 0, 1, and 2. So 2 elements and 3 elements. We define 3 predicates, input, hidden, and output. Input and output are perceptual predicates. You clearly have to perceive the input, but when you're training, you need to perceive the output. And there are 3 elements, 3 units in the input and 2 in each of the others. So those are predicate definitions. That essentially defines the layers in the graph. We then have 3 conditionals, each of them with a condition and action, in this case for the input and hidden layer, in this case for the hidden and output layer, and a function which maps the input to the hidden layer variable and the hidden layer to the output variable. We also then have this S marking, which says do a sigmoid transform at the end. So it's like having a dash there, which would do a negated transform at the end. That's all you need in order to implement that neural network. And it's basically just rules with sigmoids and functions attached. So it shares a lot of what we had before. Here's essentially how it works. Here's those 2 conditionals. Here's the graph for it. It looks a lot like the rule graph I showed earlier, though the nodes in detail, so we have a sigmoid rather than a negation here, for example. If we give it 10, 30, and 20 as the 3 inputs, process through the function node, and summarize out the input variable, we get 0.7 and 0.5. We process through the sigmoid node, and we get a transformation of that. We then go through the second layer function, summarize out the hidden variable, transform it sigmoidally, send it back to working memory, and this is in fact the correct answer. This is a sample problem from a standard web page, and this is the answer you get for it. So it's processed much like rules, but what we get here is a standard feed-forward neural network. Okay, conclusion. Feed-forward neural networks are slightly extended hybrids between rule and factor graph idioms in Sigma. So they combine the conditions and actions from rules with the functions and also the open world predicates, which we used here for reasons I won't go into, from factor graphs. And then they add one little bit. They add the ability to do sigmoid transforms. And that's what makes it happen. This immediately then provides a full architectural embedding of neural networks. We don't have to ask, like the deep learning people are asking, okay, we've got deep learning networks, that's great. Now how do we build an architecture out of that? By doing this, we now have a full architecture around this, but this is basically one memory idiom that's available. So it's potentially combinable with the rest of the architecture. Although because we violated the factor graph semantics, it isn't always trivial to do that. So it turns out the learning that we originally had of form of gradient descent isn't quite appropriate here. So we're looking at a variation on that algorithm, which will do appropriate things for these kinds of graphs. It also suggests a new view of the graphical architecture, essentially notion of extended summary product algorithm rather than factor graphs, and it sacrifices some semantic, what you consider declarative elegance, for algorithmic or procedural elegance. Just to wrap up, so here's kind of where we are in terms of the kinds of things we've been able to demonstrate in Sigma today. This is the new bit on neural networks. You can see it's a flavor of memory that fits in with many of the other flavors of memory we have, a bunch of other things we have as well. Pace suggested I added this at the end. So if you want, there's a long and detailed article on Sigma that just came out in the Journal of Artificial General Intelligence. Came out, I think, 4 days ago. It's 103 pages long, but if you want to know a lot about Sigma, this is the place to go for it. Thank you.